Hi students, now we are going to study the effect of frequency of the incident light on stopping potential. Just now in the previous video, we studied what happens to the stopping potential by varying the anode potential. Graphically, in this graph also, I have taken the positive voltage along the x-axis and the retarding potential along the negative x-axis. Okay, so along the y-axis the photoelectric current I have taken. Now, in the previous discussion, we have considered the same source, namely ultraviolet source. We fixed the frequency and we studied the dependence of photoelectric current on the applied voltage. Now, I am going to vary the frequencies, different frequencies. So, how will you vary the frequency of the incident light? I have told you. The source of light itself you have to change. Take for example, visible light source, ultraviolet light source and X-rays. X-rays have a greater frequency than the ultraviolet and the visible light. So in this combination of visible light, X-rays and ultraviolet, who is having the least frequency is what? The visible light. And the highest frequency in this combination is what? X-rays. So this is how we vary the frequency by changing the source of light. Okay students, now the nature of the graph is found to be like this. Initially for a frequency nu1, okay, then for a frequency nu2, thirdly for the frequency nu3, such that nu3 is greater than nu2 and again which is greater than nu1. So for this difference in frequencies, I find that the saturation current for the three different frequencies is found to be the same. Okay, and the stopping potentials are different. Naturally, I told you that when visible light is incident on the metal plate, how much energy it gives is different from the energy given by the ultraviolet light. Still will be greater is the energy given by the X-rays and the gamma rays. So when the frequency of the incident light itself is greater, naturally the maximum kinetic energy of the photoelectrons will also be greater, is it not? I told you that suppose if a train is coming at 60 km per hour, 60 km per hour can be somewhat easily stopped than stopping a train which is coming at 100 km per hour. Why? Because 100 km per hour speed is greater, so kinetic energy will be greater. Corresponding to that, the braking force also must be greater. The stopping force also must be greater. So my dear students, when the frequency of the incident radiation is increased means from this graph it is very clearly found that the stopping potential also will be increased. So what do we infer from this graph? The stopping potential is directly proportional to the incident frequency. Are they directly proportional or not? Yes, they are directly proportional to each other. So once again I am plotting another graph to make you understand very easily. So along the x-axis I have taken the frequency nu of the incident radiation. Along the y-axis I have represented the stopping potential. So what is the nature of the graph? What is the shape of the graph we have got? Is a straight line. But my dear students, is this straight line passing through the origin, you tell me? In the previous concept we have seen another graph, a straight line passing through the origin. That is the variation of photoelectric current with intensity. That graph was also a straight line which was passing through the origin. But this time we get another straight line which does not pass through the origin. So this clearly gives an information that there is a certain minimum frequency. See this portion, okay, this portion. There is a certain minimum frequency below which there is no emission of photoelectric current, at which and above which only there is emission of photoelectrons. Is it clearly visible for you? So this frequency, this is the blue color graph is for one metal A and this red color graph is for another metal B. So this is denoted as nu0 A and this is denoted as nu zero for a B, where nu zero is called by the name threshold frequency. Okay, threshold frequency. So what do you mean by threshold frequency? In this graph, when the frequency is 0 and a certain minimum, up to a certain minimum frequency, the photoelectron is not emitted. So beyond a certain minimum frequency only, the photoelectric emission has taken place. So this minimum frequency of the incident radiation, beyond which the photoelectric emission takes place, is called as what? Threshold frequency. This is irrespective of the intensity of the light. Even say, for example, if you keep a source of light which is less than the threshold frequency, very close to the metal, means what will happen? More number of photons will be incident, because when you keep the source very close to the metal plate, the intensity falling on the metal plate will be higher. What do you mean by intensity? Number of photons incident per unit area, per unit time. That will be greater. But if it does not have a sufficient energy, means then it cannot remove the electrons from the metal. Is it not? That is why even if the intensity of light is greater, irrespective of the intensity of the incident light, if the incident frequency is less than this threshold frequency, means no photoelectrons will be emitted. So my dear students, how to define this threshold frequency? This threshold frequency is defined as what? The minimum frequency. It is the minimum frequency of incident light. Okay, incident light. Below which, what happens, you tell me? Below which no electrons are emitted. Okay, below which no electrons are emitted. So this only is called as the threshold frequency. Okay, so now we have studied that nu equal to C by lambda in general. This is the equation relating what? The frequency, wavelength and the velocity of light. Is it not? So corresponding to threshold frequency nu naught, it can be written as C divided by lambda naught. Why I am writing this equation? This is not given in our textbook, but it will be asked in the examination. So this lambda naught can be called, as the threshold wavelength. It can be called as the threshold wavelength. So in some numerical problems, they will ask you to calculate the threshold wavelength also. For that, you can relate nu naught is equal to C by lambda naught. Okay, my dear students. So, how does the stopping potential depend on the frequency? When the incident frequency is lesser, the kinetic energy of the photoelectrons coming out of the emitter plate also will be lesser. So, easily they can be stopped. Therefore, the stopping potential also will be lesser. Okay. If the incident frequency, if the incident energy is higher, okay, energy is what? E is equal to h nu. When I say the incident energy is higher, the incident frequency will be higher, so that the photoelectrons will be emitted with very high kinetic energy, so that the stopping potential required to stop them also will be higher. Understand, my dear students? So the stopping potential is also proportional to the incident frequency. The maximum kinetic energy is also proportional to the incident frequency. But this stopping potential and maximum kinetic energy is independent of the intensity. They don't depend on the intensity, but they depend only on the frequency. Understand, my dear students? Have you understood? Now we are going to summarize. Whatever we have studied so far under the topic laws of photoelectric emission. Understand? Be ready for that. Until then, bye.